A curve has the equation x cube plus 2y cube is equal to 3xy, and I need to find the coordinates of the point at which the tangent to the curve is parallel to the x-axis. So what this question is saying that there is some curve. Let's suppose that the curve looks like this, and the curve has the equation x cube plus 2y cube is equal to 3xy, and there is a tangent to the curve that is parallel to the x-axis. This is my x-axis, and the tangent parallel to this axis would look like this. And since the tangent is horizontal, we know that the gradient of a horizontal line is 0. The gradient is also referred to as m or as dy upon dx. So this is equal to 0. And I need to find the coordinates of the point. So I need to find this point x comma y, this point here at which this horizontal tangent occurs. So what I'm going to do over here is that first I'm going to find the gradient function of this equation, and I would get dy upon dx. Now since I need to find the coordinates of the tangent at which dy upon dx is 0, I'll equate this to 0, and in that process I'm going to find the corresponding coordinates of these points. So to find the gradient function, I'm going to differentiate this equation. This is an implicit equation, so I'll have to apply implicit differentiation over here. And for that, we differentiate both sides of the equation with respect to x. The derivative of x cubed with respect to x is going to be 3x squared. For the derivative of 2y cubed, 3 gets multiplied by 2, it becomes 6, and the power gets reduced by 1, so 6y square. And whenever we differentiate terms of y with respect to x, we multiply the derivative by dy upon dx equals to 3 times xy. For the derivative of xy, we apply the product rule. This is my function u, this is my function v, and the product rule says that the derivative of this is u times v prime plus v times u prime. So the derivative of xy is going to be u is x, so x times v prime. The derivative of y with respect to x is dy upon dx plus v, which is y, times u prime. The derivative of x with respect to x is 1. So this would be equal to 3 times x times dy upon dx plus y. This equation has now been differentiated. Now all there is left is to make dy upon dx the subject. First, expanding this right hand side would give me 3x squared plus 6y squared dy upon dx equals to 3x dy upon dx plus 3y. Now shifting terms with dy upon dx on one side and non-dy upon dx terms on the other side. And that would give me 6y squared dy upon dx minus 3x dy upon dx and equals to 3y minus 3x squared. Factoring out dy upon dx on the left hand side would give me dy upon dx times 6y squared minus 3x and equals to 3y minus 3x squared. Now dividing both sides of the equation by 6y squared minus 3x would give me dy upon dx equals to 3y minus 3x squared divided by 6y squared minus 3x. I could simplify this further by factoring out 3 in the numerator and in the denominator, and that would give me dy upon dx equals to 3 times y minus x squared divided by 3 times 2y squared minus x. This 3 and this 3 cancel each other out, and I am left with dy upon dx equals to y minus x squared divided by 2y squared minus x. This is the gradient function of this equation. Now I have found the gradient function for this whole curve, and for this point the gradient of the tangent is 0. So I am going to equate dy upon dx equals to 0, and that would give me 0 equals to y minus x squared divided by 2y square minus x. Multiplying both sides of the equation by 2y square minus x would give me y minus x square equals to 0. Now adding both sides by x square would give me y is equal to x square. This is my equation for y in terms of x for this particular point. I'm going to name this as equation 2 and this original equation of the curve as equation 1. Now I'm going to substitute the value of y from equation 2 into equation 1 and that would give me an equation in terms of x only. I can solve that equation and that would give me the x coordinate of this point. So substituting y from equation 2 into equation 1 and that would give me x cube plus 2y cube. Y is x square, so 2 times x square whole cube equals to 3 times x times y. Y is x square, so 3x times x squared. Now I'm going to simplify this. X cube plus x square whole cube is x to the 6, so plus 2x to the 6 equals to x times x square is x cube, so 3x cube. Subtracting 3x cube from both sides would give me 2x to the 6 minus 2x cube equals to 0. Dividing both sides of the equation by 2 would give me x to the 6 minus x cube equals to 0. Now I'm going to factor this out, so it would be x cube times x cube minus 1 equals to 0. So this means either x cube is equal to 0 or x cube minus 1 equals to 0. After taking cube root on both sides for this equation would give me the value of x as 0. And for this equation I'm going to add 1 on both sides and that would give me x cube as 1. Now after taking cube root on both sides for this equation would give me the value of x as 1. So either the x coordinate is 0 or the x coordinate is 1 for this point. This point can either be when x is 0 or it can be when x is 1. Next I am going to find the corresponding y values for each of these x coordinates. I can substitute this x value in either equation 1 or in equation 2. If I put this value in equation 2, I would get y is equal to 0 squared and this gives me the value of y as 0. So this means that when x is 0, the y value is also 0. And this means that this point can be on the origin 0, 0. Now for when x is 1, the corresponding y coordinate would be y is equal to 1 squared and that gives me the value of y as 1. So this is the corresponding y coordinate when x is 1. And this means that this point can occur on when x is 1 and y is 1. So these are the two possibilities of the coordinates of the point at which the tangent to the curve is parallel to the x-axis. These are my two answers.